Today's episode of Wild World is sponsored by Lindblad Expeditions. Discovery is in the Lindblad DNA. Visit expeditions.com to see where in our wild world you'd like to explore with Lindblad Expeditions. Some of science's biggest questions are about our origins. How did the universe form? How did life begin? What caused the mass extinction events that reshaped life on our planet? Surprisingly, one of the best places to search for clues about these questions is Antarctica.
So there's lots of these kind of zones near the Transantarctic Mountains, for example, where there's many of these blue ice fields, as they're called, where there's, high ablation rates of the ice, and these meteorites are resurfacing there. And it's amazing because, I kind of know in my head the process of how this happens and how we think this happens. But it's still just mind-blowing when you actually go there and you see these rocks that are just sitting out there, hundreds of them, and they're all meteorites.
This is Wild World. I'm Scott Solomon, and in today's episode, we're venturing to the southern tip of our planet in search of clues about our origins and our future. Antarctica is perhaps most famous for its gigantic ice sheets and its charismatic animals like blue whales, leopard seals, and emperor penguins. But there's a lot of other important research that takes place on Antarctica, which is why there are some 70 different research stations scattered across the continent. Wadhwa is a planetary scientist who studies meteorites to learn about the formation of our universe and what conditions are like in other parts of our solar system. She's a professor at Arizona State University, where she's also director of the School of Earth and Space Exploration. Dr. Wadhwa also serves as the principal scientist for the Mars Sample Return mission at NASA's Jet Propulsion Laboratory. Her work has taken her to remote field sites around the world, including to Antarctica. Wadhwa, welcome to Wild World.
Thank you so much. It's great to be here.
So you study meteorites. What is a meteorite, and how is it different from other kinds of rocks in space like meteors or asteroids?
Yeah, so meteorites are basically space rocks that have made their way through the Earth's atmosphere. They've basically survived that process of kind of, ablation that they go through when they first sort of fall into the Earth's atmosphere. You might see fireballs during that process. So they make their way through the Earth's atmosphere and they land on the Earth and are collected so that they can actually be studied in laboratories here on Earth. So meteorites basically are those rocks that have actually survived that process of falling through the Earth's atmosphere.
So what are some of the kinds of things that we can learn from studying meteorites?
So, meteorites have been called the poor man's space probes. So it's an apt description because in a way they are rocks that sample places and times in our solar system that we really wouldn't have access to in any other way. So we have spacecraft missions that go to asteroids, and we have spacecraft missions that go to various planets and do remote observations. We might even be ambitious enough to bring back pieces of some of these places with spacecraft, and we've done that. But that's a very, very expensive endeavor, and it can, it's definitely a challenging thing for us to do. And I think there's a obvious value to that. But meteorites, in a way, provide us with a very cheap and easy way to access some of these materials. The downside, of course, is that you don't actually know very well the context or the geologic context for where these things actually come from specifically. We can broadly say, hey, these types of meteorites come from asteroids. We know that there's actually meteorites that come from Mars and from the moon. And we can actually, in one or two cases, actually pinpoint the specific asteroids that some of these meteorites come from. There's actually a group of meteorites that we think come from the asteroid Vesta, for example. And we've got some evidence, to show that basically some of the reflectance or the light reflected from Vesta matches very well the reflectance spectra or the light reflected from these meteorites. And so you can actually make some of those connections every once in a while, but for the most part, meteorites lack geologic context, but they're a great way to actually sample places and times in our solar system that we otherwise couldn't.
So these meteorites are essentially chunks of other celestial bodies, of a planet or an asteroid or some other body that is out there in space, and somehow it ended up here on the surface of Earth. And so by studying it, we can study the properties of that body. Is that essentially right?
That's essentially right. And how they get here, of course, is through impacts between some of these bodies. So asteroids collide with each other, and there's fragments of asteroids that actually hit Moon and Mars, and they eject pieces from these planets. And so these objects traverse space and eventually go into Earth-crossing orbits and can make their way to the Earth as meteorites.
So what are some of the ways that meteorites have been impactful for our history? I mean, weren't meteorites involved in kind of the formation of the Earth in the first place?
So meteorites are really, if you think about it, they really are fundamental to our very existence, I would say. People, when they talk about meteoritics and the science of meteorites, they think, oh, yeah, it's some sort of very specialized niche field. But when you think about it, it's actually not. It's fundamental to our understanding of how our planet formed, how our solar system formed, how life began potentially on the Earth, how life has evolved since that time. All of these things really have been affected by meteorites in one way or another, we think. So early in the history of the Earth, it was certainly being impacted by meteorites, and it's been suggested that some of these might have carried organic compounds that could be the precursors of life on our planet. And, we have seen meteorites that have very carbon-rich compositions. They've got amino acids and other complex organic molecules that really could have participated in that kind of prebiotic chemistry that would have been required for the origin of life.
Yeah, so it's essentially the building blocks of life may have been sort of transported here on meteorites.
Exactly. So the raw materials, the building blocks of life certainly could have been. So that's something that, we don't know exactly how life started on Earth, but there are hypotheses and certainly, lots of studies of meteorites that have shown that they carry organic compounds and the relevant kinds of building blocks, as you said. And certainly since that time, of course, after life had started to thrive on the Earth, there have been a number of extinction events on our planet. There's, I think, 5 major extinction events in Earth history. And certainly we have evidence that one of these, 65 million years ago, which is when the dinosaurs went extinct, and some 75% of all other species on Earth went extinct, we do have evidence to suggest that it was a large impact at that time that caused the global catastrophe that resulted in that extinction. And it's been suggested for, other major extinctions as well, but we don't have the evidence for some of the other ones. But I'm sure that, impacts have happened throughout Earth history, and they've had certainly local regional effects. And we know, at least in one instance, in the case of the dinosaurs, for example, it resulted in a major extinction event, which of course changed the course of life on our planet and is the reason why mammals are now dominant and human beings have evolved to where we are. So in a way, we owe our existence to meteorites.
Wow. Yeah, that is super cool. Maybe the our existence in terms of our origins as living things, as well as the fact that we mammals got a chance there.
Right.
At the end of the Cretaceous. Yeah, that's super cool. Very interesting. So you're studying something about the composition and the chemical makeup of these meteors in your lab. Is that right?
That's right. So in my laboratory, we actually have mass spectrometry instrumentation that measures individual atoms actually that make up these meteorites. And we can do lots of chemical and isotope characterization of these materials and also determine exactly when they were formed. So we do radiogenic isotope dating in my laboratory. And some of the work that we do, we look at some of the most ancient materials or inclusions in these meteorites that can tell us something about the timing of when the solar system exactly was formed. And so we're doing a lot of work in trying to understand the timescales as well as the conditions that existed in the earliest history of our solar system.
So how old are some of these meteorites?
I can tell you precisely how old.
I bet you can.
It depends. I mean, they have a range of ages, but most of the meteorites that originated in the asteroidal region, pieces of asteroids, the small bodies, they're very, very old, almost as old as the solar system itself, close to about 4.6 billion years old. The inclusions that I was talking about earlier, these have been very precisely dated to be about 4.568 billion years old. So, and we know that with a precision that's, plus minus sub-million year precision. So we can date these things very, very precisely.
That's about as old as, or a little older than the Earth itself, is it not?
It is definitely older than the Earth. So the first solids that formed, our solar system formed from this cloud of gas and dust, and the sun formed at the center of it all. And, as things cooled down in the disk, it basically resulted in the formation of small bodies, protoplanets, as they're called, which then accreted to form larger bodies like the Earth. And so the meteorites and small bodies that were the parents of these meteorites, so the original kind of asteroidal bodies on which these meteorites formed, they formed very, very early, very close to the beginning of the solar system. The Earth started to form probably within a few million years of that. And the formation process for the Earth likely extended for maybe tens of millions of years. But yes, we believe that the Earth was mostly fully formed about 4.5 billion years ago.
You're listening to Wild World. My guest is Minnie Wadhwa, director of the School of Earth and Space Exploration at Arizona State University. When we come back, we'll hear about Minnie's expeditions to Antarctica in search of meteorites. If you want to see our wild world for yourself, one of the best ways is with Lindblad Expeditions. Discovery is in the Lindblad DNA. They've been exploring the most amazing places on the planet for more than 50 years. They have the most advanced fleet of expedition ships in the world, and their trips create unprecedented opportunities for guests. Visit expeditions.com to see where in our wild world you'd like to explore next. This is Wild World. I'm your host, Scott Solomon, and my guest is Minnie Wadhwa, who has traveled to Antarctica in search of meteorites, which she studies to learn about the origins and evolution of our solar system. So there's just an incredible amount of information that you can get from studying these meteorites once you get them to your lab.
Exactly.
But of course, you got to go find them first. And so I know there are collections with meteorites, but a part of what you do in your job is to go out and search for new meteorites.
Yeah.
Right? And that sounds like a lot of fun.
It sure is. I've been very, very fortunate, actually, to have had the opportunity to go twice to Antarctica to hunt for meteorites. And meteorites are really, they're falling everywhere on Earth with equal probability. It's not that they're falling any more frequently in Antarctica or anything like that. It's just that it's easier to find meteorites, first of all, in some of the, dry desert regions of the world, including hot and cold deserts, Antarctica being a cold desert, of course. These are obviously objects that, when they interact with the Earth's atmosphere and humidity and water, they decompose quickly. And so if you want to find meteorites, the best places are dry deserts that will preserve some of these rocks for a long time. And then, of course, the lack of any kind of vegetation makes it easier to spot these things. And then Antarctica is somewhat special as well because it's got these thick ice sheets that move very, very slowly out from the central part of the continent out towards the coast. of Antarctica, and they carry along with them these rocks that have fallen on the ice over the ages. And so there's almost like a conveyor belt-like mechanism that carries these meteorites that have fallen on the ice. And it might take hundreds of thousands of years for these meteorites to get moved along with these glaciers and these ice sheets. And what happens, though, is that, if that ice sheet comes up against some kind of mountain range or some subsurface obstruction, the ice tends to flow upwards. And of course, I don't know if you've ever been to Antarctica, but they have these really, really cold and fast-moving winds called katabatic winds. They're gravitationally driven winds. And so they really ablate the surface of the ice as it's moving up. And a lot of these meteorites resurface in particular zones that are essentially called stranding surfaces, where this kind of, ice comes up against some kind of mountain range or something, and the ablation rate is high enough that these meteorites resurface. And so you can actually find sometimes hundreds of meteorites in a very, very small area. Maybe the size of a football field or something might have hundreds of meteorites there just because of this process of, carrying these meteorites along in these ice sheets and then resurfacing them. So
it's just incredible.
Yeah.
This visual that you've created of like this conveyor belt of meteorites.
Exactly.
Just sort of traveling from the center of Antarctica towards the coast and just sort of piling up or accumulating.
Exactly.
That's incredible.
Yeah. So there's lots of these kind of zones near the Transantarctic Mountains, for example, where there's many of these, blue ice fields, as they're called, where there's, high ablation rates of the ice, and these meteorites are resurfacing there. And it's amazing because, I kind of know in my head the process of how this happens and how we think this happens, but it's still just mind-blowing when you actually go there and you see these rocks that are just sitting out there, hundreds of them, and they're all meteorites.
Yeah, that's incredible. And potentially from different parts of the solar system or the universe, I guess, right? They're not necessarily from the same place.
They're not potentially. They really are from different parts of the solar system, and they've, come here from various asteroids, some of them, as I mentioned, from the moon and some from Mars. And so, yes, lots of different kinds of meteorites.
So let's talk a little bit about what it's like to do field work in Antarctica. So first of all, how do you get there?
Yeah, so it's an adventure getting there, of course. You don't just take a commercial flight out to McMurdo Station.
Yeah.
Yeah, so basically, from the U.S., you would go to Christchurch, New Zealand. That's the Antarctic base station where you prepare with the gear and whatever that you need to take down with you to McMurdo Station. And this, of course, I'm talking about the U.S. Antarctic program. And so basically what I got to do was to head over to Christchurch for a couple of times. I was lucky enough to do that. And then you get on one of these C-130 aircraft. They're really not super comfortable. They're really meant for cargo. Mm-hmm. And the one-way trip out there is about 8 hours or so. From Christchurch to McMurdo. And then usually it's at about the halfway point is when the pilots determine whether the weather is good enough and safe enough to land or not. And wow. I've known colleagues that have made that trip, half a dozen times and turned around because the weather was bad. And
oh my gosh.
And so, I was lucky though. The both times that I went, we were able to go ahead the first time and land in McMurdo. So, yeah.
So what is McMurdo like? Like, give us a little sense of like what the station itself is like.
It has sort of the feel of a mining town. It's there's all of these dormitories and a number of little bars that are there as well, and restaurants, but not quite. They have a galley, of course, where they have food, and they've got sort of research facilities. And a little clinic, a hospital. So it's about 1,000 people that are stationed at McMurdo in the austral summer. So that's typically, of course, from November through February or so. You have about 1,000 researchers that are down there, as well as a lot of support staff that are there as well to support all of the research activities. And so it's where you first, a lot of the people that actually are doing field work in Antarctica, they are doing it in different parts of remote areas of the continent, but they first, that's the base station. You go to McMurdo first, and you get equipped in terms of all of the food and gear that you're going to need in the field, and then you get out, deployed out in the field with all that equipment. And in the meantime, of course, you do have to undergo some training as well, some safety training, crevasse rescue training. And in our case, we had to get used to driving around on snowmobiles, because that was the primary means by which we would do the searching for meteorites on snowmobiles. And also, we moved around camp quite a bit when we were stationed out, when we were actually deployed out in the field. And we were out actually for almost 8 weeks out in sort of the remote parts of Western Antarctica.
That's a long time.
And yeah, it's a long time. And then, we moved camp about 5 different times in the last time that I was there. And you have to do that by, you have these sleds on which you pack all your gear, and every person has 2 sleds. Then you pack all your gear there, and you attach it to the back of your snowmobile, and you move to another site and set up camp again. And so there's a lot of gear,
a lot of logistics.
A lot of logistics.
Yeah, and so when you're camping there, you're sleeping in tents on the ice.
Yes, exactly. And so actually, those tents are not that uncomfortable. They're called Scott tents. And it's actually the same design that Scott, the explorer, Antarctic explorer, used for his expedition.
Right. Robert Falcon Scott, right? The British explorer who led 2 expeditions to Antarctica in the early 1900s.
Yeah. So these, double-walled tents that really can keep you pretty warm once you've got a little stove in your tent that kind of keeps things warm. But yeah, it's it's a small 10 by 10 footprint tent. And when I was down there, we were basically 2 to a tent, and there were 8 of us in my team. And so we were out quite a ways from McMurdo, almost, fairly close to the South Pole, actually, is where we were in the Western Antarctic ice sheet. It was quite an experience.
So what is a typical day like when you're out in that area?
Yeah, it's actually pretty exhausting work, but it's exhilarating too. We usually have a fairly early start, and it's hard to get out of your warm sleeping bags in the morning, by the way.
I bet.
Yeah. And
or at all.
Yes, it is. And also, the 24 hours of daylight, by the way, is sort of a magical thing.
Right.
And just, the fact that you're out on this kilometers thick ice.
Yeah.
And everything is so quiet. There's, it's just so quiet. But yeah, you get used to it pretty quickly. So anyway, you wake up usually pretty early in the morning and, have your breakfast, and usually just getting geared up to go out of the tent is quite an endeavor. You've got to put on, dress in layers, and you've got, multiple things to keep you warm. You have usually, I would wear like a face mask as well, the neoprene mask to sort of, because we were on snowmobiles most of the day, and you don't, the wind and the sun can be pretty harsh. And so
I imagine.
It takes a good hour and a half or so, breakfast, getting ready, and then you head on out, and you've got to basically load up your snowmobile with your lunch for the day and a little bit of gear, and then you head on out to do a search. And so we would, all of us would get together, 8 of us, and head to a particular locality near camp. And most of these ice fields where we hunt for meteorites there's been some reconnaissance trips that have been made prior. And so that there are going to be meteorites there. And so we do systematic searches where typically you'll line up at one end of the ice field, and you will systematically drive down one length and then turn around, and basically an offset of about 20 meters or so down, and basically repeat that kind of pattern until you are traversing essentially the entire ice field. And
so it's like a search party, basically.
It's basically a search party. And you can see meteorites on these ice sheets, and with practice, you can actually get really eagle-eyed, and you can spot these things from a distance as well. It depends, of course, on how big they are. But Yeah.
Because they're dark,
They're
right?
dark.
And they're on against a white background.
Exactly.
Yeah.
So they're easy to spot. And you get better, with time as well, as you sort of get used to sort of scanning the ice just to spot these things. And as soon as somebody sees a meteorite, of course, everybody goes, oh, yeah, I found one. And everybody converges on that person. And then there's a whole process that happens, which, of collecting the meteorite, which we don't actually touch them with our hands. We want to make sure that we collect them cleanly. And so we usually use these pre-cleaned stainless steel tools to pick them up, and we put them in these pre-cleaned Teflon bags, and we double bag them, and we put these identifier labels in the bags, just like the Apollo astronauts when they collected the lunar samples. The method is actually very similar. We photograph the samples before we put them in the bags. And then we also take a GPS location of where the meteorite was found. And typically then these meteorites are sort of brought back to camp and stored out. Of course, they're stored out on the ice for the 8 weeks or so that you're collecting these things. And then they are transferred over in a container ship, also, refrigerated, until they are at the Johnson Space Center, where they're opened up under dry nitrogen. And so they're kept very, very pristine. They're kept very clean. They're handled very, very cleanly. And so, yeah, they're an incredible resource. And so we treat them, of course, with a lot of care.
Sure. Yeah. So 8 weeks down there, about how many meteorites were you able to find?
So in my field season, the last time I was there, we collected about 350 meteorites. Yeah, and that's about, I would say, average. I think in some of the field seasons, they've collected over 1,000. In others, maybe might be less, just depending on whether the conditions were very, sometimes, of course, we have these really, we have blizzard conditions and, high winds. And so you can't really go out in that kind of weather. And so I've known field seasons when they've been kind of trapped inside tents for most of the season. So it just depends.
That sounds miserable.
I know.
How cold does it get?
Well, during usual working conditions, I would say it was about negative 20 or so Fahrenheit. That's about sort of normal, negative 10 to negative 20.
Wow.
But with the winds, the wind chill, it makes it feel like it's negative 60 or 70 sometimes. That's when it's the conditions when you really wouldn't want to be outside. And that is brutal, because the moment you step outside, your breath freezes and your eyelashes get iced over, and it's pretty rough.
This is Wild World. I'm Scott Solomon, and I'm speaking with meteorite expert Minnie Wadhwa about her expeditions to search for meteorites in Antarctica. When we come back, I'll ask Minnie about how she became interested in studying meteorites and about some of her other adventures doing fieldwork around the world. If you want to see Antarctica for yourself, one of the best ways is with Lindblad Expeditions. Discovery is in the Lindblad DNA. They've been exploring the most amazing places on the planet for more than 50 years. In 1966, Lars Erik Lindblad chartered a ship and brought the first non-scientific travelers to Antarctica. Today, Lindblad operates the most advanced fleet of expedition ships in the world, and their trips create unprecedented opportunities for guests. I'll be journeying to Antarctica in 2024 with Lindblad and the Rice University Traveling Owls. Want to join me? Visit alumni.rice.edu/travelingowls or expeditions.com to get more information and to book your cabin for the journey of a lifetime. Welcome back. I'm Scott Solomon, and I'm joined by Minnie Wadhwa, Director of the School of Earth and Space Exploration at Arizona State University. So, tell me a little bit about your childhood. You grew up in India.
I did. I grew up all over the place in India, actually, because my dad was in the Indian Air Force. And so we moved every 2 or 3 years. And so we lived in a number of places in North and South and Western India. And so one of the things that, was nice about it, though, was that it sort of made me comfortable with change and made it, I found it easy to sort of get used to different places and meeting different people from different parts of the country. So overall, it was a pain at the time. Of course, you had to sort of uproot and, leave your friends behind and make new friends. It was, as a kid, that can be a little bit traumatic. But in retrospect, it was actually, I think it was a really good thing. It was a wonderful experience to be able to see so much of the country and meet new people.
I understand that for a while you wanted to be an architect. Is that right?
I did. I kind of thought that's what I wanted to do. And in a way, the Indian education system, it's very different from here. You have to actually decide fairly young, almost straight out of high school, exactly what you are going to be and do. And there's not really any do-overs. So, you have to decide if you're going to be an engineer or if you're going to be a doctor or whatever you want to do. You have to decide basically at age 17. And so I thought that that's what I wanted to do, be an architect. But also, there's these very, very kind of well-defined cutoffs for grades. And if you don't have those, you don't get into certain tracks. And so I actually did not make it to architecture school, but then I started to think about other options, and I knew I liked science. And, I thought maybe physics or chemistry might be interesting. I liked them. I liked biology too, but I didn't enjoy the dissection part of it, and, and actually a little bit squeamish about doing that kind of thing. And certainly the sight of blood was not for me.
Yeah.
So I thought about it, and I sort of, in India, you usually go to university in the same town that you live. It's not like here. And so I went to the university close by, and I investigated a little bit in terms of what my options were, and I found out about geology, which I hadn't really known was in there. I didn't even know, that I could actually study geology in college. And I found that, hey, it's really kind of a cool thing that you could apply the principles of physics and chemistry towards understanding the natural world. That's really what it is. And so I thought that was really kind of what I wanted to do, because I was always fascinated by the natural world in any case, and rocks, the Himalayas, mountain ranges that were close by. And I always was fascinated by doing things outdoors. And so I certainly felt like I would enjoy doing the field work. But it was one of those things where when I visited the department, the professors there and the people there, they were all male professors. There was not a single woman professor in that department. And there were very few women who were students in that department. And so it was kind of a little bit strange to me to be in that kind of environment, but I kind of felt like this is the subject that I wanted to study, and so that was fine. I was sort of dissuaded a little bit by some of the professors saying, "Hey, field work might be tough. You may not be able to do it," and that only kind of made me want to do it more. So I don't know.
Nice. And then when you came to the U.S. for grad school, did you find that changed much when you were here?
No, this was, I hate to say it, but this was like almost 3 decades ago now. So
yeah.
things were very different. And I came to grad school, and I found that there were not very many women in my class, in grad school, in my cohort. And so there were maybe, a few more women who were faculty, but maybe I would say between 5 and 10% of the faculty were women. And I was actually very fortunate in that my PhD advisor was actually a woman. And I had no idea, actually, when I accepted grad school to work with her. That she, I thought it was. I thought her name sort of. I wasn't familiar with it, and I thought it was a man actually. And
interesting.
But I wrote to her when I first found out that I was admitted, and I said, "Hey, I'm excited to be working with you." And she still laughs about it because she said that I addressed the letter, "Dear Sir." And so she put me right for sure, because it was just not in my experience. I hadn't really encountered that in India, and so I just assumed she was a man. But most of the faculty were men, as it turns out. But things are changing for sure.
Yeah. So how has that experience affected the way that you do science today, and training the next generation of students?
Well, I mean, I recognize the value of mentorship and the value of representation for sure. And I think that's a very powerful thing for students to be able to see a woman who's doing the kinds of things that I'm doing, and especially a woman of color. I think it's empowering for many of the students who come from backgrounds that are traditionally underrepresented in the sciences. And so I do take that seriously in the sense that I know that, to me, it made a huge difference seeing a woman faculty member and recognizing, hey, that's a pathway that might be open to me. So it can be very empowering, and I recognize that, and I try to leverage it to open doors for others if I can.
And you're married to Scott Parazynski, who has also been a guest on Wild World. And I understand that you guys had a very special moment together in Antarctica.
Yes. This was such a coincidence, actually. I decided to go to Antarctica during a sabbatical year. And at the same time, Scott actually happened to have the job of basically the chief medical officer for the Antarctic. And so he happened to be in McMurdo by coincidence over the same 48-hour period when I actually got out of the field, when we were taken out of the field. So at the end of the field season. And, it could have gone very, very different way in the sense that because the way the weather is and things change, and we'd, of course, had the date on which we were supposed to get out of the field move around quite a bit as well. But as it turned out, we came out of the field at a certain time, and Scott happened to be in McMurdo at that point. And he, I guess, had some plans that he had not told me about, but he sort of felt lucky, and he felt like maybe we would cross paths in Antarctica. And so he asked me to marry him at Scott, actually at Scott's hut was the location.
Oh, wow.
In McMurdo. It was amazing. I know. And, at that point I'd known Scott, I guess about close to 2.5 years or 2 years or something like that. And I, we knew that we were going to get married at some point, but this was, well,
that's quite a proposal.
It was quite a proposal. One that I couldn't refuse for sure.
You're listening to Wild World. I'm Scott Solomon, and I'm speaking with planetary scientist and meteorite expert Minnie Wadhwa. In our final segment, we'll learn about some of the ways that meteorites might be important for our future survival. I love to travel and experience new places, and I've had the great pleasure of joining several Rice Traveling Owls trips operated by Lindblad Expeditions. Each of these trips, from the Galapagos Islands to the Belize Barrier Reef, Baja California, and the upper Amazon River, has been absolutely incredible. Lindblad Expeditions make nature and wildlife accessible to anyone. Visit alumni.rice.edu/travelingowls or expeditions.com to learn more and to see where in our wild world you'd like to explore next. This is Wild World, I'm Scott Solomon, and my guest is meteorite expert Minnie Wadhwa, director of Arizona State University's School of Earth and Space Exploration. Now, you've done fieldwork in some other places too, and I understand that in 2017 you were part of an expedition in Iceland, and you were actually in an accident there. What happened?
Oh gosh, yeah. This was, this was a great project that I've been looking forward to this field trip for a while, and we were going to collect Icelandic lava flows that were analogs for lava flows on Mars, and we wanted to try to understand basically the history of water in some of these igneous rocks. And so, yeah, I went there in August of 2017 with one of my colleagues from the University of Iceland. He's a geologist and very familiar with some of the rocks in the region that we were going to be collecting them from. And as it turned out, we were driving in this field vehicle, an SUV style vehicle, and my colleague was driving it, and he and his postdoc was sitting in the front, and I was sitting in the back with one of my friends accompanied me. Her name is Cyan Proctor. She actually, by the way, very interesting person. She's the one who flew with Inspiration 4 in 2021.
Sure, yeah.
And so an incredible person. And she's like, she loves to travel, and Scott was supposed to have gone with me on that trip, but he just had published his book, and he was on a book tour on the East Coast. And so he couldn't come. And because he couldn't come, Cyan actually was volunteered to just come along and help document some of the things about the trip. And she's very passionate about science communication. And so she was going to help with some of the science communication aspects of the trip. And so she and I were sitting in the back. We'd driven something like 5 or 6 hours, sort of north and east of Reykjavik. And this is a fairly remote part of the country, and we'd stopped for lunch at this wonderful site that had these amazing rock formations and columnar joints, actually, in basalt that are really incredible. We'd finished lunch and we were just starting to get back out on the road, and there was a caravan of cars, which is really kind of unusual. We were in a very remote part of the country and not very many people around, but there'd been several people that had stopped at the same lunch spot that we did, and they were all getting out at about the same time. And so my colleague started to accelerate the vehicle to get past these cars, and one of the cars in the caravan sort of slid out of their spot to try to overtake as well, and they crashed into us, and the vehicle just kind of did a few flips. It rolled over, and I unfortunately was not wearing a seatbelt because we'd just been coming out of getting our lunch, and I was taking some pictures out the back window, and I hadn't had the chance to buckle in. And basically I was tossed out of the vehicle. Wow. And so it was a vehicle ejection, and I actually don't remember anything from that incident. I actually don't even remember half an hour before the accident. It's something that's sort of completely wiped from my memory banks.
Wow.
But probably a good thing, because I kind of remember waking up in the middle of the night and not knowing where I was, but I was in the emergency room in Reykjavik. They had to airlift me out of the field, but I had, a lot of broken bones and fractures, mostly on my left-hand side. I had a completely fractured pelvis and a punctured lung, and I was in bad shape. I actually was very, very lucky to have survived, because Scott tells me that, in his emergency room doc experience, not very many vehicle ejection accidents, basically that there's not a good survival rate for those types of accidents. And so I was just very, very lucky. And it was an incredible year of recovery after that. It was, in a wheelchair for about 4 months and lots of physical therapy. But yeah, I was I was very lucky to have survived, and then I was very lucky to have had some very, very good care.
Sure.
And Scott was able to, he flew out of New York, that same night, and was able to be there, and actually advocated for me to be flown back to the U.S., which I think, certainly, I don't know, I don't think I would have been able to do that if I'd been by myself. And I was able to get really good care at Mass General Hospital and then rehab in a great facility after that. So it really helped me get back on my feet. And I've been able to do a couple of half marathons since then. And
that's fantastic.
Hike the Grand Canyon. So it's
Wow.
I'm doing okay. Yeah.
How would you say that experience affected your approach to fieldwork? Do you do anything differently these days?
Gosh, I make sure to wear my seatbelt. That's for sure.
Yeah, I bet.
No, but other than that, I would say no. I mean, I actually, as I said, I don't remember it at all. And my friend, actually, Cyan, I think she still has a little bit of PTSD when she's sitting in the backseat of a car. She tells me that it's kind of still a little bit, because she remembers the whole thing. She was belted in. She remembers when the vehicle was sort of rolling over.
Oh my gosh.
But, I don't remember anything. And so, I mean, the only thing, like I said, I mean, there's not really much that I could have done except, yes, I mean, I think, I know that seatbelts save lives for sure. So
an important public safety announcement.
Yeah, exactly. Yeah. But I'm still very much excited about, being out in the field and being outdoors. And I love doing that. And Scott and I love to be sort of exploring and hiking.
So we've talked a little bit about what we can learn from meteorites about our past and the history of the universe. But do you think they might also be important for our future? I mean, we know, as you said, that a meteorite struck the Earth 65 million years ago and nearly wiped out life on Earth. Do you think something like that could happen again?
It's not a matter of maybe, it's a matter of when, right? It's going to happen. I mean, just probabilistically, that's going to happen sometime in the future. It's whether we're prepared for it or not. I think this is the first time in human history, or actually in Earth's history, not human history, but Earth's history, where there's a species on this planet that can actually do something about that. And so, I don't know if you heard about the DART mission.
Oh, right. NASA's double asteroid redirection test.
Yes, exactly. That essentially was a test to see whether you could divert the course of an asteroid by actually impacting it with some force. And so we have the capacity to actually take action, but we have to kind of know where they are. And so there's programs basically to map the locations of many of these near-Earth asteroids in particular. And so, there's an effort to sort of try at least above a certain size threshold to really map every single object, say that's over 140 meters or something like that. So the goal is to try to map as many, close to 99% of those in the next few years. And so I think we're trying to make the effort to make sure that we can stay safe in the future. And, it may not happen for another, 10 million years, or it might happen tomorrow. So,
What about some of the other ways that space rocks might be important for our future? Things like, mining of asteroids, for example.
There is definitely some value in the potential utilization of the resources that these objects may have. At the current time, at least, I think the return on investment on some of these things is there's not a great business case to be made for it, just because of the cost of doing something like that, of mining these objects for, say, rare metals or something like that. It's not something that is going to kind of earn anybody a profit at this point, probably, until there's some real investment in technologies and ability to do those kinds of things. But it's in the future, maybe that might be a possibility. I don't know if you've seen The Expanse, but
Sure.
That's the kind of thing that could potentially happen in the future.
Yeah, they have people living in the asteroid belt, right? The belters who are out there and they're mining resources. Yeah. Yeah.
Right. But I think that's probably, we're a long ways from that at this point.
So if you're standing out, say, in Antarctica and you've just discovered a meteorite, you're holding it in your hand, how does that make you feel? I mean, do you feel like you're better connected to the universe? Or does it just kind of make you feel small and insignificant?
I've been lucky enough to have the opportunity to hold meteorites in my hand through much of my career, and being out in the field and being able to actually recover them, rocks that have never really been touched by human hands before. That is an amazing feeling, right? And it is mind-blowing when you think about it, where these rocks have been, where they came from, how much time was involved in actually forming these rocks. It is mind-blowing, but it's one of those things where I love what I do because it sort of is inspiring, to think about we as human beings having the capacity to actually tease apart the history that's locked in these rocks and learn something about our very origins. And we know so much at this point about the history of our solar system, about the history of our planet and how it evolved and all of these kinds of things. I mean, it's possible because, we know where to look and we can actually tease apart some of that history. So yeah, it is inspiring to me.
And now, in addition to studying meteorites, you're also working on the first mission that seeks to bring samples back from Mars to Earth, right?
That's something that's been a dream of mine since I was in graduate school because, I started my grad studies studying meteorites from Mars. And that was in itself I think that was really kind of what put me on the course to being a meteoriticist really are these meteorites from Mars. I had no idea that they were these rocks that we thought were from Mars. And so, just being able to kind of study these rocks that came from another planet and, vicariously being a geologist on Mars, that's pretty cool. But I always dreamt of getting some actual rocks back from Mars that are, not meteorites, rocks that we could actually carefully select where we understand the geologic context and bring those back. And we're actually doing that. We're doing that right now with the Perseverance rover. It's collecting those well-characterized rocks, and we're going to bring them back in 10 years. And I'm just super excited to be, the lead scientist for that mission, and it's going to be amazing.
That is incredibly exciting. That'll be a moment in history for sure.
It will. It'll be historic for sure.
So what kinds of things do you hope to be able to learn from the samples collected directly from Mars that you haven't been able to learn by studying pieces of Mars that come to Earth as meteorites?
Yes. So, the enduring question about Mars is, was there ever life that originated on that planet? Was there ever life that existed on that planet? And so the big question that we hope to answer when we bring back those rocks from Mars is to understand whether there's evidence of ancient life in these rocks. And I think it's going to fundamentally change our perspective as human beings if we find some evidence like that. And on the other hand, if we don't, that tells us something as well about how planets evolve. And we certainly think that Mars had water in the past. And so, whether or not life originated, I think could be a really fundamental finding from these rocks. And then, of course, I think that fundamental finding does not happen in a vacuum, right? I think we want what I'm really excited about is learning about Mars as a planet. How did it form? How did it evolve? This geologic evolution. What was the history of water? What was the history of its atmosphere? All of that has bearing, of course, on whether life ever arose there or whether life existed there. And so I think just understanding all of those things about our neighbor, our neighbor planet, is going to be fantastic.
Well, Minnie Wadhwa, thank you so much for being on Wild World and telling us all about your fascinating work.
Thank you. It was great talking.
That's it for this episode. To learn more about Minnie Wadhwa's work on meteorites, check out the show notes where we'll have links to her website and her fabulous TED Talk. We'll also have links on our website, wildworldshow.com, along with some photos of Minnie and her work in Antarctica. You can listen to Wild World anywhere you get your podcasts. Follow us on social media at @WildWorldShow. This episode was sponsored in part by Lindblad Expeditions and the Rice University Traveling Owls. Learn more about their trips to Antarctica and other exciting destinations at expeditions.com or alumni.rice.edu/travelingowls. This episode of Wild World was produced by 3Wire Creative. I'm Scott Solomon. Join me next time as we explore another part of our wild world.